Now, I am going to discuss about the design of lacing system. Now, in earlier lecture we have shown what are the force coming on the lacing and what are the failure modes are coming for lacing system for the built up member, and how to calculate the number of bolts, how to calculate the thickness of the lacing, width of the lacing, and how to decide the spacing of the lacing bar, what should be the length of the lacing bar. All these things have been discussed, but for designing we have to make a systematic way, so that step by step we can design. So, first I will discuss the steps which can be used for design of a lacing system. It is a very lengthy process, so we should remember the steps chronologically, so that we can design systematically a lacing system entirely. And after discussion of the steps, we will discuss about the one software has been developed by my students. I will discuss how a software can be developed and how the lacing systems can be designed, right. And if time permits, we will go through one example partly. Okay. So, let us come to the design steps. So, first what we will do, we will choose a lacing system, means either we will choose a single lacing or double lacing, that we have to first decide, because the design procedure will be entirely changed for single lacing and double lacing, because the number depending on the single lacing or double lacing, the force acting on the member will be different, and accordingly the force on the the number of bolts, the dimension of the lacing system will be changed. Similarly, if single lacing if we provide, what will be the radius of gyration and what will be the slenderness ratio, and for double lacing what will be the slenderness ratio, that also will be calculated in different way. So, if we decide first the lacing system, whether it is single lacing or double lacing, then it will be better to proceed further. Next is we have to decide an angle of inclination with the axis of the compression member. Angle of inclination means this angle theta. So, as we told earlier that theta should vary from 40 to 70 degree, and generally we try to keep theta from 40 to 45 degree to get maximum efficiency of the lacing system. Then once we decide the lacing system and its angle of inclination, then we can find out the gauge distance and the distance between two members. Means if we see, if this is a channel section facing back to back, then we can find out this is gauge distance. If this is gauge and this is S, then we can find out the distance between these two from gauge to gauge, that is A. So, find the distance A between the bolt center, that can be found, and for a given shape we know what is the gauge distance on each side, right, and also already we have decided what should be the spacing, so that IXX and IYY become same. So, that has already been decided, and the size of the section has also been decided, whether it is channel section or I section, that also has been decided, and whether it will be channel section back to back or toe to toe, that has also been decided earlier. So, according to that we can find out the value of A, which is the distance between bolt center. Next is, so A will become basically S plus 2G, where S is the clear distance and G is the gauge distance. Now, we have to find out the length of length between two lacing. So, which is called spacing, clear spacing, spacing between two lacing, right. So, how do we find out the length? Length means this one. So, we know this value A. A means the distance between bolts. So, if we know A, then we can find out the value of this, right. If this is theta, this will be theta, right, and this will be if this is theta, then A by L by 2 will become tan theta. So, L by 2 will become A by tan theta. That means, L will become 2A by tan theta, right. So, L, the length between two lacing members can be found for single system as 2A by tan theta, where this is L by 2 and this is L by 2. So, L can be found for single lacing. Similarly, for double lacing it will be simply this L, not this one total. Total is for single lacing and this is for double lacing, right. So, for double lacing system it will be A by tan theta. So, this is how the spacing between two lacing can be found. Then another we have to find, that is the length of the member, length of the lacing. So, length of the lacing also we can find out, because we know if this is theta, A sin theta will be the L. So, L I can make A by sin theta. So, in case of single lacing or double lacing, the length of lacing can be found from this geometry, that is A by sin theta. This is how we can find out. Next, in step 3, we can find out the slenderness ratio of each component and check for slenderness ratio. So, we now know the L. So, and RC minimum, we know RC minimum about this direction, the individual radius of gyration of the section, the minimum radius of gyration of the individual section. So, L by RC minimum, and it should be minimum of this 50 or 0.7 lambda max, that we have to check, right. If it is not, then we can, what we can do, we can either reduce the length of spacing by changing the angle of inclination, or we can change the section size, right. So, this is what we have to do, so that the local buckling of the member can be arrested. Local buckling of the member can happen, and that can be taken care by providing this restriction, right. In step 4, so once we find out the length of each lacing, then I can find out the effective length. Now, effective length will be either 7 if it is a single lacing system with bolt end, if it is double lacing system it will be 0.7 L, and if it is welded system it will be 0.7 L. So, we can find the effective length of the lacing member in step 4. Now, in step 5 we can find out the thickness of the lacing. So, for lacing member we need to know length, then thickness and width. These are the three things we need to know. Already we knew the spacing between lacing member and angle of inclination, right, theta. So, the thickness can be found from this, that T should be greater than L by 40, where L is the length of the lacing member, and this is true for single lacing, and for double lacing it will be greater than L by 60. So, from this I can find out a suitable thickness of the lacing system. Now, we have to check for slenderness ratio. So, we can find out the maximum slenderness ratio of the lacing system, and generally lacing systems, in case of lacing system, lacing members are either flat plate or maybe angle or maybe channel, right. In case of flat plate, we have calculated already in earlier classes that lambda lacing will be LE into root 12 by T. So, it should be less than 145. So, for flat plate, lambda can be found from simply this formula, that is LE root 12 by T, and we have to check it should be less than 145. Now, if it is not less than 145, what we can do? We can increase the thickness of the lacing. If we increase the thickness of the lacing, then lambda lacing will be reduced, and the we can make the lambda lacing below 145, right. So, in step 7 we will calculate the compressive strength of the member we can calculate. Then in step 8 we can calculate V. So, in step 7 compressive strength means the P, the total compressive force or whatever it is coming on the member, that we can find, and then the transverse shear V is 2.5% of P. So, that can be calculated, right. And then after finding out the transverse shear, we can find out the force in lacing, because transverse shear, if it works like this and if lacing is like this, then what will be the force on this component, that can be found, right. Now, coming to step 9, we can find out the compressive stress and tensile stress of the lacing system, and we have to check that this compressive stress and tensile stress is less than the permissible compressive and tensile stress. So, we know permissible compressive stress of the lacing member FCD value, right, for a particular radius of for a particular slenderness ratio and for a particular grade of steel, and also we can find out the tensile stress and the permissible tensile stress, and the developed compressive stress and tensile stress also can be found, and we have to check whether it is less than or not. If it is not less than that, then we have to increase the section size. Section size means either we have to increase the thickness or width of the flat plate, or if we use angle section, then we have to increase the section, right. Once it is done, we can go for connection. So, if we use bolt connection, then we have to choose a suitable bolt diameter, and we have to find the minimum width B of the flat plate, right. So, B can be found from the bolt diameter, that 3D will be the minimum flat width, and then number of bolts required also it can be found, that will be simply N is equal to F by R, and F is the force on that member means lacing member, right. So, number of bolts can be found from the bolt value. So, before finding out the number of bolt, we have to find out the bolt value R, and depending on the spacing and means pitch distance and edge distance, and whether it is single shear or double shear, R will be calculated. So, once R is calculated, we can find out the number of bolt. Now, in step 11, we will design the end connections for the lacing system. That means, we will check for the number of bolts whether it is sufficient or not to withstand the load, and if we go for weld connection, we will check whether the length of weld connection is sufficient or not to withstand that load, and this length of the weld will be decided on the basis of weld strength and the force acting on the lacing member. Depending on that, the lacing welding size and welding length will be decided. So, this is what the steps we have to follow to find out the lacing dimensions and its configuration, right. So, 11 steps we have discussed here. We have to chronologically follow these steps more or less, and then we have to find out one by one, and finally, we have to find out what should be the final angle of inclination of the lacing, what is the lacing size, what is the spacing, and what is the number of bolt or length of weld and size. This is what final output we have to make. Now, this is a sample software output we have shown here. In fact, one of my student has developed this software, where the lacing member can be designed. Now, the most important part of this is that how to make a GUI to take the input. Say, I am showing this example to give an idea about how to develop a GUI, means how it should look and how user friendly one can make a GUI, so that a user can use this and find out the design and can find out the dimensions of the lacings and its design details. Now, suppose first if we come to the type of column. Now, these few options have been incorporated in the program. One is column containing angle, means it may be box section or some other section, and column containing channel. Okay. And channel will be facing each other, means facing toe to toe or channel back to back. So, these are the options we have. Now, if we click on column containing angle, then this will this pop-up button will come, where we can find out a particular section, and these sections are taken from these sections and their properties have been taken from SP6. From SP6, the different section size has been taken and their properties, which are stored in the library of the software, and then when we are clicking a particular size of the section, its properties will be taken. Now, then the spacing has to be decided, because spacing will be decided on the basis of Ixx equal to Iyy. On that basis, we have to decide spacing. So, the spacing will be provided here, and yield stress of steel we have to provide. We have to select yield stress of steel, and then whether we are going for angle lacing or flat plate, that also we can decide. So, these options are also incorporated in the software, that we can provide not only plate means flat plate, but also we can provide angle lacing. And then another options we have created, that is whether it is single lacing or double lacing, because if we go for single lacing, then it looks like that, and then accordingly the calculations will be done, and if it is double lacing, then its calculation will be different. Then we have to go to the load, what is the compressive load is coming and what is the height of column, that has to be defined. And here you see we have given a help button. In help button, if you click, then we will get the all the design criteria, means what are the design steps and how design has been done, the theory has been provided here. And in flow chart, the how step by step it has been progressed, that has been shown in this flow chart. And if we click in analyze, then it will go for analysis of the system. So, here you see, if we select the column containing channel, then there are two options we have, the channel facing each other and channel opposite to each other, right. So, that will be taken care, and others will be similarly we can consider, say, angle section or plate section for lacing system, then single system or single lacing or double lacing, all these things will be similar. Only thing is, when column containing channel, so all the channel properties means all the properties of the channel sections as given in the SP6 will be taken. Here channel opposite to each other has been considered. Here another option has been considered, that is, if we consider double lacing system, then how the orientation will be done, that has been shown here. So, the program can take care the design of double lacing system as well, right. Now, we will go through one example. So, the design steps whatever we have discussed will be followed in this design example, and in this design example the previous example has been considered. Previous example means in lecture 35 we have considered a certain section, means against a certain load and length of the column, and then we have considered that ISMC 300 section and back to back with a 184 millimeter spacing, that has been decided. So, on that basis we will try to find out the details of lacing. So, coming to the example, if we see that design a laced column 10.5 meter long to carry a factor axial load of 1000 kilonewton. The column is restrained in position, but not in direction at both ends. Provide single lacing system. Use two channel section placed as back to back. Assume steel of grade Fe 410 bolts and bolts of 4.6 grade. Design the lacing system with bolt connection and design the lacing system with side weld connection. So, for two cases we will consider. So, if we recall the design example provided in lecture 35, we can see that we obtain ISMC 300 channel section and having a spacing between these two as 184, and channels were placed back to back. So, this is what already we have calculated. Now, we will calculate the forces coming on lacing and the dimensions of lacing. So, if we come to that, first what we can find out? We can find out what should be the L by R, right, and this L by R should be less than 0.7 into L by R, right. Now, this L by R already has been calculated as 93.35, right, and L0. So, for design of lacing we have considered this example, that is a design of laced column of 10.5 meter long to carry a factor load of 1000 kilonewton, and the column is restrained in position, but not in direction at both ends, and provide single lacing system. This has been told, and use two channel section placed as back to back, and assume the steel of grade Fe 410 and bolts of grade 4.6, and design the lacing system with bolted connections and design the lacing system with welded connections, right. So, basically this is the example which has been done earlier in lecture 35. So, same example has been considered here, and in lecture 35 we have seen that how to calculate the spacing between two members and how to decide the section size, that has been discussed in lecture 35, and we have seen that ISMC 300 section is sufficient to take care the load, the given load, and 184 millimeter spacing is sufficient. So, this is what earlier we have calculated. Now, we will come to the design of lacing system. So, coming to design of lacing, first we will find out the angle of lacing. So, what should be the angle of lacing? So, that has to be decided. right. So in first step we have seen that we have to assume the angle of lacing. So, here we can assume say angle of lacing theta as 45 degree, right, and for this channel section the gauge distance was given in SP 6, it is 50 mm, right. So, the distance between bolt to bolt means, because the channel sections are placed like this, back to back it was placed. So, distance between two bolts can be found now. This is S and this is the bolt distance, this is G and this is G. So, distance between the bolt, center to center of the bolt, which is called A in general, this A we can find out as S plus 2G. So, that will become 184 plus 2 into 50, right. So, this is what we will find out, that means 284 millimeter, right. Now, once we find out A, we can find out the spacing between lacing L, because we know the angle of inclination, we know A, right. So, we can find out the spacing between lacing bar. So, L 0 will become 2 A by tan theta, right. So, 2 into A is 284 by tan 45 degree, right. So, this is becoming 568 millimeter. So, L 0 means spacing between two lacing, this has been now decided as 568 millimeter, right. So, once this is done, we can find out L 0 by R y y. Okay. So, L 0 by R y y should be less than 0.7 L by R. Okay. This L by R was calculated earlier as 93.35, that means 0.7 into 93.35. So, this is becoming 65.34, right. So, L by R now we can find out as L 0 by R y y, we can find out as L 0 is 568 and R y y is 26.1, right. So, this is becoming 21.76 and this should be less than 0.7 L by R y R. So, that is 65.34 or it should be less than 50, right. So, as we found L 0 by R y y as 21.76, which is less than this. So, the spacing between two lacing member is okay. So, L 0 is okay, right. Now, we will find out the maximum shear V. As we know, maximum shear will be 2.5% of the compressive load. So, we can find out 2.5 into 10 cube by 100. So, 25 kilonewton, right. Now, in each panel transverse shear will come in each panel as V by N, that will be 25 by 2, that will be 20.5 kilonewton, right. Now, we have to find out the force, compressive force in lacing bar. So, V we are getting 12.5 kilonewton and we have to now find out the force on this force, right. So, this we can find out this force as V by sin theta, right. So, V we got 12.5 by sin theta is sin 45 degree. So, this is coming 17.67 kilonewton. So, compressive force in lacing bar we can find out this. Now, the size of lacing flat we can find out. We can choose lacing member as a flat plate. If we choose that, then we have to decide the thickness and width of the lacing member as well as the length of the lacing member. So, to find out the thickness of the lacing member, we have to find out the length, and also to find out the width of the lacing member, we know that it should be dependent on the diameter of bolt. So, we can assume some diameter of bolt, say diameter of bolt as 16 mm. So, width, the minimum width as per the clause 7.6.2, minimum width will be 3 into 16, okay, 48 mm. That means, we can provide say 50 mm width, and thickness we know that will be for single lacing system, it will be 1 by 40 into length between two plate. Now, length between two plate we have to find out. Now, length between two plate can be found as we calculated length as A by sin 45 degree. If we go back to earlier lecture, we can see that length can be found A by sin 45 degree, that this is coming A is 284 by sin 45. So, it is coming 402. So, thickness will become 1 by 40 into 402, right. So, that is coming 10.05 millimeter. So, the thickness we can consider as 12 mm, because minimum is 10.05 mm. So, thickness of the plate can be decided from this. Now, R we know that T by root 12 for flat plate. So, that we can find out as thickness we have considered 12. So, we can find out R, the minimum radius of gyration will be 3.464, right. So, L by R we can find out, L was calculated as 402 and R was calculated as 3.464. Okay. So, this is 116 and is less than 145. So, it is okay, right. So, from slenderness point of view, this is okay. Now, we will find out the compressive stress FCD. FCD of the member can be found because slenderness ratio is given. Now, from table 9C we can find FCD as 94.6 minus 94.6 is the FCD value corresponding to 110 and 83.7 is corresponding to 120 by 10 into 6. So, 88.06 MPa FCD value. Now, once we find FCD value, we can find out the design compressive strength. Design compressive strength PD we know AE into FCD. So, AE is the cross sectional area of the flat plate, which is B into T into FCD value is 88.06. So, this is coming 52.84 kilonewton. So, design strength of the compressive, the lacing member is 52.84 kilonewton, which is greater than the axial compression force on lacing member, that is 17.67, which was calculated earlier. So, this is how we can check that the design strength is more than the actual force coming on the lacing member. So, the size of the lacing member is okay. Now, we can find out the tensile strength. As per clause 6.2 and 6.3.1, we can find out the tensile strength as first we will find out due to rupture of the critical section, that is 0.9 into B minus D H into T into Fu by gamma m1. So, that will be, so TDN we can say, TDN will be 0.9 into 50 minus 18 by gamma m1 is 1.25 into T is 12, Fu is 410. So, this is coming 113.36 kilonewton, right, and the strength due to gross yielding TDG, we know we can find out Ag Fy by gamma m0. So, Ag is 50 into 12 into Fy is 250, gamma m0 is 1.1, so 136.36, right. So, the design tensile strength will be minimum of these two, which is 113.36 kilonewton, and this is more than the axial tension or compression coming on the lacing bar, that is 17.67. So, hence safe, right. So, this is how we can find out, right. So, for today's lecture, as we do not have much time, so we can conclude here, and before concluding again, if I repeat the steps, whatever we have done in the workout example is, first we have found means we have assumed first what is the angle of inclination, and according to that we have found the distance between bolt, that A, then we have found the spacing between the lacing member, then we found the lacing dimension, that is thickness, width and length from the geometry and from the design criteria. Then we found the compressive strength, design compressive strength of the lacing bar and design tensile strength of the lacing bar, and we have seen that the design compressive strength and design tensile strength is more than the actual force coming on the axial force coming on the lacing bar. Now, the lacing bar will means if one lacing bar is in compression, another lacing bar will be in tension. So, for both the cases the magnitude of the force will be same, that means for compressive force and tensile force will be same for the same lacing bar, and this is what we have checked, and also we have checked the minimum slenderness ratio, means the which is means the slenderness ratio of the column member means it is less than the permissible slenderness ratio. Also we have checked the slenderness ratio of the lacing member is under the permissible limit of the lacing member, permissible limit of the slenderness ratio. So, these are the checks we have done. Next what we will do, we will go for connections details, right. Okay.